students, I wanted to go into depth and talk about SN1 today. It is going to be a longer video, so short disclaimer. It's not that I want to intend to make it super long. It's just that I want to show you different examples. I have 4 examples in this video, and I want to show you when you're going to form a pair of enantiomers, when you're not going to form a pair of enantiomers, because I know that's a key thing that confuses a lot of students, and so I definitely wanted to cover that in this video to at least show you different SN1 reactions. So let's get into it. So SN1 is for substitution, okay, and it is a very key reaction again that you're going to see in OChem 1. It doesn't mean that you're never going to see it in OChem 2, you will, but it's definitely one of the more major topics covered in OChem 1. So let's go over the features together. What are the features of an SN1 reaction? So the key features. 1, it forms a carbocation. And I didn't write it, but it's going to be multiple steps. And in SN2, you're going to only have a 1-step reaction or a concerted reaction. In SN1, that's not what happens. You're going to have multiple steps. And the first step is going to be that the leaving group leaves and you're going to form a carbocation. And usually what you're going to form is a tertiary carbocation, because that's, in terms of SN1, that's the carbocation that you want. I don't want to say that tertiary are the most stable carbocation, because you have allylic, which is even more stable. But in SN1, what you generally see being the most stable is the tertiary, and that's what it wants to make. What else do you see? Well, since it has a tertiary carbocation, if you have, again, pay attention, if you have 4 different groups, this is basic first week OChem stuff, then you're going to have chirality. If you have chirality, you're going to produce enantiomers. And SN1 is known for making racemic mixtures, which is a pair of enantiomers. Now, I want to emphasize that not all cases are going to form enantiomers. And again, that has to do with the chirality of the molecule. If the molecule of the carbocation and stuff that you're forming, if you have 2 methyl groups on it, for example, then you're not going to be chiral, you're achiral, and therefore you're not going to form enantiomers. So don't worry if that didn't make 100% sense right now. I'm going to have examples in this video. I'm going to have 4 different examples. I'm going to show you when you're going to form enantiomers and when you're not, so that way at least it's going to be clear when you form enantiomers and when you don't. Okay, another key feature, you need an excellent leaving group. Again, you want to form a carbocation, so you need something that's going to leave and form that carbocation. So that's why you need an excellent leaving group. And again, you don't need a really strong nucleophile. And if that doesn't make sense to you, it's because I'm not really discussing E1 in this video. I won't. But generally, when SN1 reactions occur, you can also have E1 products. And so usually with E1, you have like a weak base. And that's what I mean. You don't need something strong. You don't need a hydroxide, for example. Usually strong bases are with E2 reactions. So you don't need a strong nucleophile for an E1. Like you can have a methanol and you're fine. You can have a water and you're fine. It doesn't need to be strong. Okay, so what about solvents? So again, solvents is a huge thing in OChem 1. So you have polar protic and polar aprotic. I'm not going to discuss that in this video. I will make a separate video discussing polar protic and aprotic. But usually SN1 will have a polar protic solvent. And likewise, SN2, the opposite, right? SN2 is going to have a polar aprotic solvent. So I'm not saying that SN1 will never have an aprotic solvent. I'm just saying it's more common for SN1 to have a polar protic solvent. Okay, so at the end of this, you might be thinking, okay, why is it a 1? What is the 1 for? I'm glad you asked. So what does the 1 mean? It refers to the kinetics. So this reaction is unimolecular, and it depends only on the substrate. So it is independent of the nucleophile concentration. So if I double the concentration of the nucleophile, and that goes to rate law stuff, that's not going to affect the reaction. What is going to affect the reaction, again, is the substrate. So now that you know the key features and what SN1 is, let's dive in to the actual mechanisms, because that is what you need to know, the nitty-gritty for SN1. Now, before I get into the mechanisms, I just want to say in the mechanisms, I didn't draw the inorganic product. Like, I drew the organic product. Like, I drew the enantiomers, or I drew the alkane, and the things that you really want to see in organic chemistry. If your professor asks you to also draw the inorganic product, yes, you will have to write an HBr is formed, or an HCl is formed, or methanol is reformed, or whatever. But what I'm doing in this video is showing you only the organic product. So let's get into the video. This is the first example. So in these examples, as you can tell, you are going to form enantiomers. Why? Again, you have 4 different groups. So let's get into what happens. So the first step is that the bromine is going to leave. And then you form your carbocation. In this case, it's perfect. It's a tertiary carbocation, and that's what you want for an SN1. Then the methanol is going to go and attack. And then what is going to happen? The methanol can attack from the front, or it can attack from the back. If it attacks from the front, it is going to be in bold, as denoted below. If it attacks from the back, it's going to be in dash. So now let's go with the one with the front. It attacks from the front, but notice that it has a positive formal charge. And again, if you don't know how to calculate formal charge, I have a separate video on that. But the formal charge is +1 on the oxygen. So the plus sign should have probably been a little closer to the oxygen. So just know that if your professor is really stringent, make the positive sign a little closer to the oxygen. And then what's going to happen? Well, the bromine that you have from the first step is negative. I should have drawn the negative charge on there, so I'll do that in a second. Well, the bromine is going to go and attack and grab the hydrogen. And then those electrons between the oxygen and the hydrogen are going to go to the oxygen. Okay. And then the same thing's going to happen from the back. The bromine is going to grab the hydrogen. Then those electrons are going to go to the oxygen. Okay. So I'll draw those in, but I think it's going to probably go away because of the way that I have the video set up. But just know that you have a negative charge there. Just draw that on your paper whenever you are doing the exam. Okay. And as you can notice, you formed a pair of enantiomers. You have an R and you have an S. I'm not doing R and S in this video. Again, you can check out my other video for that. But you have a pair of enantiomers, and as you notice, you have 4 different groups. You have a methyl group here, you have the OCH3 here, you have the ethyl group, and then you have this group here. So you have 4 different groups, and that is why you had a chiral center, and that is why you have a pair of enantiomers. Okay, let's keep going. So in this example, I'm going to give you with a water, because water could also be. But as you know, in the first step, the bromine is going to leave. It's going to form a carbocation, as you can see. Then water is going to go and attack. And then afterwards, water can attack from the front, or water can attack from the back. In the front, I have it in bold. In the back, I have it in dash. Again, the water is going to have a positive formal charge, the oxygen more specifically. Again, have the positive sign a little closer to the oxygen. And then what's going to happen, the bromine, again, put the negative charge, is going to go and grab the hydrogen. It wants that more electropositive density. Remember, bromine is really electronegative. So it's going to grab the hydrogen, and then those electrons between the oxygen or the hydrogen are going to go to the oxygen. Okay, the same thing is going to happen for the back. The bromine is going to grab the hydrogen, the electrons are going to go to the oxygen, and again, you're going to have alcohols produced in both. Okay. Now, let's go over examples in which you won't have enantiomers. So it seems very similar to the first thing that we did. And I even wrote a note. There is no stereochemistry because there's no stereogenic center. This molecule is not chiral. It is achiral, and therefore there are no enantiomers formed. So drill that in your head. If you don't have a chiral center, then you're not going to have enantiomers. So again, the bromine's going to leave. You're going to have your carbocation formed. And yes, you need to write that positive charge there because that's showing you that you have a carbocation. The methanol is going to go in attack. But look, I don't have any stereochemistry. The bromine's going to grab the hydrogen, and then the electrons are going to go to the oxygen, and I still have my OCH3. But notice that again, I have no stereochemistry because again, I have two groups that are the same. I have two methyl groups, and therefore I have no chiral center. Okay, so now let's do the last example. I have my chlorine. My chlorine's going to leave. Again, my methanol is going to go in attack. And then I have a positive charge for my oxygen. And then my chlorine is going to grab the hydrogen. The electrons are going to go to the oxygen. And again, I have my OCH3. And again, this group is the same as this group. So you do not have a chiral center. So I hope that that makes sense of why sometimes you will have chiral centers and why sometimes you won't have chiral centers. It depends. If you have 4 different groups, you'll have a chiral center. If you don't have a chiral center. If you do not have a chiral center, you do not have enantiomers. If you have a chiral center, you will have enantiomers. Okay, one more point that I want to stress that I didn't make emphasis on is that notice that in this example, I still had an SN1 reaction, but this is a secondary carbocation. And that's crucial for you to know because it's not that, oh, you always have to have a tertiary. If not, it's not going to happen. That's a lie. You can have an SN1 reaction with a secondary. It's just that it prefers to have a tertiary. Okay, now if you have a primary carbocation, on the other hand, that's more than likely going to be an SN2 reaction because that's what SN2 wants. It wants everything done in one step. And again, I will have another separate video on SN2. But for SN1, usually you're going to have a secondary or tertiary carbocation, tertiary being even better. And you will have enantiomers, again, if you have a chiral center. And you will have, again, that racemic mixture if you have a chiral center. You form your carbocation in the first step, and that is why you have multiple steps. It is not a concerted reaction like SN2. You have an excellent leaving group because, again, you want to form that carbocation. You don't need a strong nucleophile. Again, I showed you the example of having a water or having a methanol. And again, this can happen in both solvents, but usually it's going to be a polar protic solvent. And if you think about it, since you have a carbocation, that those protons kind of stabilize that carbocation, and that is why usually you have a polar protic solvent. And again, the 1 is for the kinetics, meaning that is unimolecular, and it depends only on the substrate. So again, if you like this video, it takes time to create this content, so please follow, like, share, comment. Let me know your thoughts and questions. Happy studying, and thanks again for watching.